Hello class, and today's lesson is going to be on circuit diagrams. And we'll intro series and parallel circuits as well. So circuit diagrams, they're just a simplified drawing of an electric circuit, but we simplify it to just make it easier to see. That's the whole idea here. We follow a few key rules. One, every line that you draw is just straight. Use a ruler if you can, that'd be nice. If you have to bend or anything, just make sure it's done 90 degrees so we have nice square boxes. And all of the wires, which are drawn as lines, they should never cross over each other. You don't cross the lines. Anytime that there's lines that seem like they're crossing, that's actually what we would refer to as a junction. So that's actually a wire that is splitting into pieces. So if you don't want wires to be splitting, don't draw them over top of each other. And there are some symbols for us to use. Don't worry too much about a lot of these things. We'll practice these and you'll get a handle for them. It's pretty straightforward. It's just keep it tidy, keep it clean, and it should be simple. That's the big idea. It should be easy to see. So let's take a look at some of these symbols. You can see, let's start at our top here. We're dealing with the cell. You see that there's a long end and a shorter end separated by a small space. We also call cells a source. These sources, they provide electric energy for the circuit. If you look just below that, there's a battery, and you can see it actually is a similar symbol to the cell. You just stacked two of them together. It's because that's what a battery is. A battery is multiple cells that are connected together. Since cells are sources, batteries are multiple sources, we just call it a source as well. Most of the time, I'm going to refer to the source of electric energy a source instead of calling them cells or instead of calling them batteries. I'll tend to call them sources. And I almost always draw my sources using the battery symbol. Now we have switches to turn things on and off. And so there are two modes for a switch. There's the open mode and there's the close mode. You can see with the open mode that the ends are not connected, that there's actually a gap in between. But in the close mode, like you pulled it down and you've connected both ends. So just for clarity, when a switch is open, that is off. And when a switch is closed, that's on, because electrons can flow through the conductors or through the wires, but they can't go through empty space. Now, the next one, that this one, the resistor or the load, this is a really multi-purpose tool. A load is any object that uses electricity in the system. And we have so many different loads. Anything that uses electricity is called a load. You could also call it a resistor. Common ones that we use in our circuit diagrams will be light bulbs or lamps and motors, or we'll just call them resistors. So resistor or load, and that's this spiky symbol. Some people like to do a specialty symbol for a light bulb and a specialty symbol for a motor, but I don't think those are actually necessary, so we're not going to deal with that. The next two, the ammeter and the voltmeter, these are devices that are used to measure amounts of stuff going through our circuit. The ammeter, you can see, is a circle with an A, measures the electric current, or how much electricity is running, how much electricity is flowing through a thing. We always set up our ammeters in series, and we'll learn more about that in a bit. A voltmeter is circle with a V, and it's a device that measures the energy. We actually call it is the energy per unit charge that's through the component of the system. So it measures how much energy something is gaining or how much energy something is losing across a particular component. Voltmeters are always hooked up into something we call parallel. The last one that I'll include here is a fuse, and you kind of see it almost looks like a tilde or a curly sort of line. And a fuse is like a one-time use switch. It's a device that will break the circuit when there's too much current running through it. So it's a device that always starts like a switch that's closed, but when too much runs through it, it'll break and turn into a switch that's open. Yeah, so fuses are kind of like one-time switches, or they're conditional switches. We're not going to use them too often, but they show up sometimes. All right, let's talk about the importance of a circuit or circle. in a circuit, the free electrons in the conductors can move around in one direction to create a flow of electrons. And devices can use the energy of this moving electricity to perform their functions. Since all of our atoms in conductors have electrons, if you push a couple of those electrons, say to the left, for example, those electrons moving to the left are going to jump and move over to the next atoms in the conductor. But they already have atoms. So the electrons will repel with electrons because they're both negatively charged, and we know two negatives repel. So those pushed electrons are going to push the electrons on the next atom and push those ones over. And then those ones push the one that's just next over to that, and those ones push the ones that are next over to that. And so pushing some electrons pushes the nearby electrons, and that causes a chain reaction where all of the electrons in a whole circuit begin moving. However, and this, if you have everything hooked up in a circle, this actually works perfectly, because you push some, it pushes the rest, and it goes around and around and around and around until it keeps this path of continuous pushing. But if there's a place for if there isn't a place for the electrons to go, for example, if I took that circuit or that circle and I cut a piece off, the electrons don't have a place. They can't jump across the empty space. So they get stuck at the end. And if any electrons are stuck at the end, well, they're going to be repelling the electrons that were coming back at them. And so they repel, push back, and so if there's a push to the left, the ones are stuck, won't move anywhere, so they push back to the right. That just means there's a push to the left, a push to the right, and that balances out and nothing ends up moving. So it stops any electron flow. So here's a little visualization of that. If we take a look at the first diagram with the red arrows on it, you could start at the source. The source pushes the electrons. You see they go up, they turn the corner, they go across one of the loads and across the second load, and these loads use some of the energy, but the electrons keep moving through, and they turn the corner again, and it comes back. And since it's a full circle, they can make their way back to the opposite end of the source, and they can begin going through that loop again. And there's always space for the electrons to move, because if they push, well, everything else just moves around, and that means the whole thing just begins going in a nice circuit, a nice circle of movement. But if we take a look at the second picture, the source is trying to push the electrons, but if you followed along, you'd see that there's actually a big break after the first load. And so now the electrons have nowhere to move, so the ones at the end of the break, they're actually going to be pushing back, which means the source tries to push forward. The gap where the electrons are stuck, they're going to push back, and those two pushes cancel each other out. No electrons are going to move. And the same is going to happen with the opposite side, right? The negative tries to pull in, but there's nothing to pull, and it all just nothing happens. There's no circuit. So a broken circuit or an open circuit is a circuit that doesn't function. A closed circuit is a circuit that is functioning. So let's take a look. If you follow the current, you start from the positive or long end of the source, and you trace your finger in a path that never backtracks until you reach the negative end. Each different path you take is a unique loop in the circuit. If we take a look at our first one, there's only one loop. You put your finger on the long end and you trace yourself around, as I've shown in blue arrows, and you have yourself a nice happy little loop. But some of our circuits are a little more complicated. If you take a look at the second diagram, you can put your finger on the long end, follow along, and you notice after the first load you get to a part where there are two ways the electron can go. It could head up along the green arrows, or it could head further to the right along the red arrows. One electron can't go in two paths, so it'll only choose one of those paths, where other electrons might choose the opposite. And this is where you notice you can have two totally distinct loops. So one example is following the purple loop. You head down, cross the first load, and then you head up following the green arrows, and then you're going to continue towards the source, so you head back to the left following the blue arrows again and back to the negatives. And then so there's our purple loop. The yellow loop follows down and to the right across our first load, following the blue arrows. But when we get to the junction, we keep going right, and then we head up following the red arrows, and then back to the left following the red arrows, and then we rejoin the current coming in from green, going across with the blue arrows again across the last load and back in. So we have our yellow loop. So this one circuit has two distinct loops in it, a purple loop and a yellow loop. But it's still one completed circuit. Some teachers or some people, they actually say that the electrons flow from the negative end towards positive, because repelled from negative towards positive. And that's true if we're talking about the direction of electron flow. The direction that I draw all of my arrows is in the direction of something that we are called conventional current. And conventional current was the convention as defined by Benjamin Franklin, and we didn't change because we don't need to. So I'm going to stick with conventional current for all of my diagramming. It's not really an issue though. You don't have to worry about it. So let's look at a situation. Let's make a circuit diagram for this. So here's a little light bulb. You can see that there's two D-cell batteries. There's a light bulb. There's some wires connecting to the housing of the light bulb. There's a switch that you notice that the wiring isn't quite connected, so it's an open switch. And then there's more wiring that leads back to the D-cells. So what would that look like? Well, I would probably start off at my D cells. So I'm starting off here at the bottom. Here are my two D cells. Right? You can see there's my little battery. And then I just follow along. My D cells move into a light bulb. So I move it forward, and I decided to draw it up into a little resistor or a load, which is what a light bulb is. Then I keep going, and I'm going to move my way back a little bit, and there's my switch, and it is open, just like we see in our picture of the flashlight. And then from that switch, we move back to the D cells. So there's an example of our light bulb, or sorry, our flashlight done this way. Now, some circuit diagrams may end up looking different, but they're actually the exact same circuit. If you took a look at the first two, they look a little different, but you might notice I actually just rotated it 90 degrees. It's the exact same circuit. It's just rotated. There's nothing different about it. For the third one, that one I'm like, okay, Mr. Westgard didn't rotate that. The order of things is changed. But it's the same circuit. Even with the order of things changed, this doesn't change how it works. All that matters is that they remain in the same loop. And this is why we're going to see where this comes up. But when it comes, if we look at our previous example here where I've color-coded my loops, so long as you keep the color coding, it's fine. So in this case, there's just simply one loop. There's only one loop. So all of these would be yellow loop, for example. And if I have the exact same components all in the same color of loop, then it's all the same circuit. So this one we have a battery, a switch, and a load all in one loop. It's the same circuit, even though the circuit diagram looks a little different. So there's a lot of flexibility you can have with the circuit diagram as well. It doesn't need to look exactly the way it does in reality. So let's talk a little bit about series circuits. Components that are in series are attached in a direct connection or in the same loop to each other. So any electrons that are going to flow through pieces in a series flow through them in a sequence. So we can see R1, R2, and R3 are all connected up in a line in our first diagram. 1, 2, 3 in a line, that's clearly something in series. Now R1, 2, and 3 in our second diagram, they're not in a line, but if you follow your loop, there's only one way to go, through all three of them in a row. And so I chose to highlight them here. We can see, oh, it's just yellow loop, it's yellow loop. These are the same circuits. These are series circuits. Now, parallel circuits are the ones that are a little trickier. Components that are hooked up in parallel are actually attached in separate loops. Electrons that flow through like any electron can flow through one of the components, but not both of the components at the same time. So if we followed our finger from our positive source, you'd be able to move your finger up through R1 and then back, or up through R2 and back, but you would never be able to start at the source with your finger on the source and go through R1 and R2 without backtracking or going over something twice. So both of these diagrams, they look a little different, but they're the same. Let's take a look at the circuit diagrams. Right, we can see R1 is in this little yellow loop and R2 is in this purple loop. And in the second diagram, R1, while it's a little bit odd to see, it is in just its own yellow loop, and R2 is in its own purple loop. The two circuits are actually identical, even though my diagrams are a little different. So let's see if we can practice this. Let's see if we can turn this into practice. Like, how can I draw my own circuit diagrams? So let's start here. Like, can I draw a circuit where the two resistors are in series, but they are in parallel with a third resistor? So to start this off, I probably want to start with like, okay, it says two resistors in series. So I know I have to draw two resistors in series, means the same loop. So it's like one after another. So bam, bam, resistor, resistor. Now they're in parallel with a third resistor. I don't want to add that third resistor on the end of that because that would be series. So I'm going to take my third resistor and I'm going to put it off to the side because that would be parallel, or that's next to it. So there we go, because then when it's next to it, that'll make its own loop. Then I'm going to just use some straight lines to tidy up. So here we go. You can see straight lines. Now I can have some pieces that are started to be part of the same thing. And here is my last piece. I just add in a source because a circuit won't work without a source. And there we go. Now, did I do this right? Do I have two resistors in series and the third one in parallel with those two? Let's check. The ones in series should be in the same loop, and the third one should be in a different loop. So I'm going to use my highlighter, and I'm going to color it again. Following from the positive of my source, I go up, across, down my two resistors and back, and up, across, and down my resistor and back. Let's see. There we go. I have my two resistors in series in my yellow loop, and my third resistor is in purple loop. Purple is separate from yellow. It is in parallel. And that is how we do circuit diagrams. Let's practice those up. We're going to be using circuit diagrams to help, and this coloring of loops to help us understand how these components interact together. And we're going to be practicing with more of this as the week goes on. All right. I hope you have a good day, everybody. Please try the two worksheets that we have today. Goodbye.